Summary questions 1.3. Okay, so the first one I've drawn on here already. Question 1 is all about photons, and question 1 asks us, list the main parts of the electromagnetic spectrum in order of increasing wavelength. It's really a question from GCSE, but at GCSE you're more likely to be given gaps to fill in. Theoretically at A-level they could ask you to just sort of list it out. The only way I can think to do it is with a mnemonic, and I've invented this one, which may help some, may not. Roger might invent really useful X-ray glasses. Okay, so radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. So Roger might invent really useful X-ray glasses. Don't forget that this end of the spectrum has long wavelengths and low energy, so long and low. Okay, so I sort of, my head, for some reason I sort of exaggerate that and it seems to stick. Long and low. And then at this end, the gamma end, it's short and high. Short and high. So short wavelength, really lots of peaks in a small distance, and high energy, very high energy. Okay? Part, you'll also find, before we go on, sorry, to part B, you'll also find, if you look in the book, there is a section here that gives you some of the wavelengths, etc. Okay. Part 2, or it's part 2 of that question. So move this up. Okay. It says calculate the frequency of light of wavelength 590 nanometers. And then afterwards it asks radio waves of a different length, so we'll do that in a second. So 590 nanometers. Now I wrote it down. Really I should have put what units it is. Wavelength we mark as lambda. Okay, now for this we're just looking at frequency we want. Well, for this we need the de Broglie equation, which is wavelength, done that terribly, equals speed of light over frequency. Now we want to rearrange like this because we've got wavelength, we want frequency, and our algebra says we can just move this up to there and that down to there, so we will move it about and we will get that frequency is equal to the speed of light divided by wavelength. So we can plug in what we've got here and we can say that therefore F is going to be equal to 3 times 10 to the 8, which we should all know is the speed of light. Okay, 3 times 10 to the 8 meters per second over 590. Now make sure you get the units right on this. Nano, so if it's nano we're talking times 10 to the minus 9. Okay, when we do that calculation you should find that you get 5.08 times 10 to the 14 hertz. And we know that infrared is possibly going to be in the sort of, that's the right kind of range for infrared. You can look on here to get an idea. Oh, this is in millimeters, this is in wavelength, but you could look at the frequency of that kind of light and a reference and you should see that's in about the right area. Okay, let's just move the paper up. So, part 2. Okay, we've got doing it again, but this time the wavelength is a radio wave of 200 meters, so a very long wavelength. And then we can say therefore frequency is equal to, again, 3 times 10 to the 8 for speed of light divided by 200. And you should get an answer out of 1.5 times 10 to the 6 hertz. Much lower frequency, which we expect for radio waves. Okay, question 2 says, with an aid of a suitable diagram, explain what is meant by electromagnetic wave. Now, if this comes up, it's just sort of a drawing exercise really. What you're after is this diagram here, and basically you just draw a line forwards, and then I just happen to have other colours, which is handy. You draw a wave on that line like that, and then you draw a wave sort of coming towards you and away from you like that, and then you can add a little effect to make it clear which way it's going. In real life, the magnetic part is actually much smaller than the electro part, but for these purposes that's more than adequate. Very simple to draw. Then you would just highlight that this is, say, magnetic. Question 2. This is electrostatic or electric field. And put an arrow so you realise it's a wave that's travelling, and you could even put direction of wave if you wanted to, but pretty much that's it. That answers that question. Okay, so for part 3, it says light from a certain light source. Let's give some space to work in. Okay. Light from a certain light source has a wavelength of 430 nanometers. So as soon as I read it, I write it down. Now, one thing that's been tripping people up is the standard form for nanometers. So another suggestion is that don't ever write nanometers before you start really thinking about the question, and while your brain stood on the sort of reading part, where you're not going to skip over something by mistake and forget to do something. Write it in standard form. Then you know you've got what you need. It says part A, the frequency of the light. We need to calculate the frequency of the light and its wavelength. Oh, sorry, we know its wavelength. The frequency of the light of this wavelength. So it's the same question as we've got above. We can rewrite that out. 3 times 10 to the 8 over 430 times 10 to the minus 9, and you're going to get an answer out of, checking my results, 6.8 times 10 to the 14 hertz. Again, it's in the right range. Part B, the energy of a photon of this wavelength. So photon energy, we're going to need to use the equation, the photon energy equation, that links frequency to energy, and it links it via Planck's constant, which we must remember is 6.63 times 10 to the minus 34 joule seconds. So the equation is E is equal to HF. Must remember that equation. Very important. So in this case, E is going to be equal to 6.63 times 10 to the minus 34 times the frequency, 6.8 times 10 to the 14. Theoretically, we could have rewritten Planck's constant, this equation here, as E is equal to H. Now F, we know, is C over lambda, so you could have written as HC over lambda. So if we hadn't done the first bit where we'd already calculated frequency, or you wasn't sure about your frequency calculation, then you could use this equation, and that is just a combination of this one and this one, or that one there. Okay, but we did calculate it, so we're going to use it, and that would give us an answer of about 4.6 times 10 to the minus 19 joules. 10 to the minus 19, we know we're in the right ballpark for joules of energy for photons. Okay, last question then, question 4. Let's move this all right up. Okay, question 4. It says, calculate the frequency and energy of a photon of wavelength 635 nanometers. So it's exactly the same as what we've done there, but this time they're asking it in just one part of a question. So again, we're going to write wavelength is equal to 635. We'll work on that method we've been using there and write it straight away in standard form. So, because it's nanometers, it'd be times 10 to the minus 9. And then we can straight away say that F is equal to C over lambda, which is equal to 3 times 10 to the 8 over 635 times 10 to the minus 9, which is going to work out to 4.7 times 10 to the 14 hertz. And then we can say that E is equal to HF, which is equal to 6.63 times 10 to the minus 34 times the frequency, which we just calculated there, 4.7 times 10 to the 14. Do that calculation and we will get an energy out of 3.1 times 10 to the minus 19 joules. Part A done. Exactly the same as the one before. Very easy questions. Realistically, these are very simple things. Just make sure you identify what it's asking for. Photon energy, frequency, or wavelength. It's the only three things you're going to do. There could be a question where they sort of quite cleverly say to you, prove Planck's constant is 6.63 or something like that. But then that will just be using this equation. Part B. A laser emits light of a wavelength 635 nanometers. So we're talking the same wavelength as above, so don't need to write anything down. In a beam of power 1.5 milliwatts. Calculate the number of photons emitted by the laser each second. Now, this equation is very, very similar, but basically we say that the power of the laser beam is equal to, so the power is equal to NHF. Okay, so a little bit of rearranging. We want N, so for N, as the number of photons, this HF is exactly as it would be here. So power is equal to number of photons per second. Basically, this is energy, this is rate of energy being used. So there's always going to be a per secondy part added in because we're looking at power. Okay, so we want to work out N. We're going to need to take this to the other side, and we're going to get power over HF. So we get a power 1.5. Now I didn't follow that standard form idea myself there, but I could have done times 10 to the minus 3. So milli times 10 to the minus 3 over HF, 6.63 times 10 to the minus 34 times 4.7 times 10 to the 14. We have actually calculated HF there, so I could have just written that underneath, but that won't always be the case. And when you work it out, you get an answer of 4.84 times 10 to the 15. And what's the units in? Well, it's photons per second. N is theoretically a count. Okay, so what have we done there? We were basically told that a laser beam has this wavelength and is rated at this power. From the wavelength we were able to calculate the frequency. From the frequency we were able to calculate the energy of the photons of that frequency. And then by knowing the energy consumed over time, or the power, we were able to calculate how many photons would be passing out of or being emitted from the beam every second for that amount of power to be transferred. And that's the end of them summary questions. Thank you very much.